Welcome back to Talk Tensors. Ready for another deep dive?
Always.
Today we're looking at this paper, Langevin Soft Actor-Critic, Efficient Exploration Through Uncertainty-Driven Critic Learning. It's all about continuous control reinforcement learning, getting robots to move smoothly in the real world.
Yeah, like not just doing those clunky pre-programmed movements.
Exactly. So you sit into this paper plus some background info on the techniques they use. Stuff like Langevin Monte Carlo, diffusion models.
Right.
So what's our mission for this deep dive today?
Well, we want to try to understand how this new algorithm, LSC, tries to balance exploration, so trying new things, with exploitation, using what it knows to get rewards. And of course, we want to see if it lives up to the hype, if it's as sample efficient as they claim.
Meaning, does it learn faster with less data?
Exactly.
Okay, so let's start with the basics. What is LSE and what makes it stand out?
LSC stands for Langevin Soft Actor-Critic. It's a type of reinforcement learning algorithm, but it's specifically designed for continuous control tasks.
So not just picking from a set of fixed actions like press left or press right.
Right. Instead, think of it like controlling things with a range of values, like the angle of a robot's joint.
So it's like the difference between choosing left or right and smoothly steering a wheel.
Precisely. And the big claim here is that it can learn much faster with less experience, which is a big deal in reinforcement learning.
Absolutely, because training AI can take forever. But why is continuous control so tricky anyway?
Well, there are a few key challenges. Imagine a robot arm trying to grasp an object. It has to smoothly control all those joint angles at once.
Right, that's a lot of variables to juggle.
Exactly. Traditional algorithms struggle with those complex actions.
Okay, so challenge number one, dealing with a ton of moving parts. What's the next hurdle?
The next big one is something called overestimation bias. It's like the algorithm has this critic that judges how good its actions are, but sometimes it gets a little too optimistic and overestimates how good certain actions are.
So like a cheerleader instead of a coach.
Yeah, and that can lead to bad decisions based on bad information.
Makes sense.
Okay.
Okay, what's the third challenge then?
This one's all about learning efficiency. A lot of traditional methods need to see the same scenario over and over to update their knowledge. They're not good at squeezing the most information from each experience.
That sounds inefficient.
It is. It really slows down learning.
Okay, so three challenges then. Complex actions, an overly optimistic critic, and slow learning. So how does LSC tackle these?
Well, that's where things get interesting. LSIC has some really innovative solutions.
Okay, let's hear it. What's the first trick?
First, it tries to address that overestimation bias. Instead of just looking at the average value of an action, LSA considers a range of possible outcomes.
It's like a probability curve.
Right. It's factoring in the uncertainty and risk, not just the best-case scenario.
So a more cautious and realistic critic. I like that. But how does it explore all those possible outcomes?
That's where Langevin Monte Carlo comes in. It's
Yeah.
a way of sampling different points in that distribution of values.
So instead of picking the single highest average value, it's looking at a wider range of possibilities.
Exactly. It's like taking a random walk through the landscape of potential outcomes.
Interesting. So it sounds promising, but does this actually lead to better performance?
Well, that's what we're going to find out. But first, we were just talking about LSE using Langevin Monte Carlo to get a better grasp of uncertainty, looking at multiple possible values for each action.
Right. What's next?
Okay, so the next big thing is multimodal Q posteriors.
Multimodal Q what now?
Yeah, it's a mouthful. But imagine the AI's understanding of how good actions are is like a landscape with multiple peaks. LSE doesn't want to just get stuck on one peak.
It wants to explore them all.
Exactly, to find the best possible solution.
So it's like having a team of explorers, each one's searching for the highest point on the terrain.
Perfect analogy. And to do that, it uses a technique called parallel tempering. It runs multiple learning processes, each with a slightly different temperature. Yeah, you can think of it as controlling how willing each process is to jump between those peaks in the landscape.
Gotcha.
Higher temperatures, more exploration, lower temperatures, more focus on refining the best solutions they've found.
Oh, I see. So it's like having explorers with different risk appetites. Some are bold and adventurous, others are more cautious and methodical.
Exactly, and that leads to more robust learning and exploration. But remember, we also talked about that challenge of slow learning.
Yeah, how does LSC handle that?
Well, that's where the diffusion Q action gradient comes in. It's a way of generating extra training data, like creating imaginary practice sessions for the AI.
So like the AI is daydreaming about different scenarios to learn from.
Yeah, kind of. It uses something called a diffusion model to create these synthetic experiences.
And are those just random?
No, not at all. And that's the key here. LSAC refines the actions in those imagined scenarios using its current knowledge of what's good.
So it's targeted practice based on what it already knows. Pretty smart.
Exactly. And by adding this extra carefully crafted training data, LSAC can learn way faster than methods that only use real-world experience. It's like giving the AI a turbo boost.
That's awesome. But does this actually work? All this sounds good in theory.
Well, that's the exciting part. The paper shows LSE doing really well on these standard benchmarks like MuJoCo and DeepMind Control Suite.
There's like those virtual obstacle courses for AI agents, right?
Yeah, where they control simulated robots to do different tasks.
Right.
And it outperformed or matched the top algorithms out there, like DSCT, which was considered the state of the art.
Okay, so it can handle the standard tests.
But it gets even better. They also tested LSCC on these mazes designed to be really tricky for exploration.
Really put it through its paces, huh?
Yeah, and it was able to find multiple paths to the goal in these mazes while other algorithms got stuck exploring just one option.
So that uncertainty-driven approach is really working.
Seems like it. All those clever techniques we talked about are paying off.
That's exciting. So it sounds like LSA is a big step forward for reinforcement learning. But why should we care about an algorithm performing well in a virtual maze? What does it mean for the real world?
Great question. These might seem like games, but they actually capture a lot of the challenges of real-world robotics problems.
So faster learning means robots that can adapt to new situations more quickly.
Exactly, and that makes them more useful in more applications.
Like what?
Everything from manufacturing and logistics to healthcare, even space exploration.
Wow. So this isn't just about robots solving puzzles. It's about making them more versatile and capable in real-world situations.
Exactly. Plus, better exploration could lead to AI finding more creative solutions to problems.
Instead of just sticking to the same old routines.
Right. It could have a huge impact on fields like design and engineering, even scientific discovery.
Okay, you've sold me.
Yeah.
LSE sounds pretty amazing.
It definitely has a lot of potential.
But are there any downsides? I mean, no algorithm's perfect, right?
Oh, definitely not. And LSAs does have some areas for improvement. For example, all those techniques, the parallel tempering, the diffusion models, they can be computationally expensive. It might need more power and memory than simpler algorithms.
So not exactly lightweight. Anything else?
Well, the paper focused on model-free reinforcement learning, which means LSAC learns directly from experience without building a model of the environment.
Right, that's different from those model-based approaches where the AI tries to create a mental map of its surroundings.
Exactly. And model-based methods can sometimes be more efficient, especially if you have some prior knowledge. It'd be interesting to see if some of LSA's ideas could be adapted to a model-based setting.
Interesting. So LSA is a promising step, but there's still room for exploration and improvement.
Always. That's research for you.
Always pushing those boundaries, finding those new possibilities. It's always cool to see how these researchers are pushing the limits of AI. So let's move on to our favorite segment, novel notions. What kind of intriguing ideas did this paper spark for you?
Well, one thing that comes to mind right away is like, could we apply LSAC beyond continuous control? I mean, the paper focused on robots, smooth movements, but what about problems with like discrete actions, choosing from a set of options, you know?
Instead of controlling a robot arm, it's more about making decisions.
Yeah, exactly. The way LSE deals with uncertainty, explores possibilities, it seems like that could be super valuable in those situations too.
So like an AI playing chess.
Right. But with a much deeper understanding of the risks and potential outcomes of each move.
Wow. That's like the AI is considering all the what-ifs before it makes a move.
Yeah, exactly.
Cool. Any other ideas?
Let's see. Another thought I had was taking this idea of parallel tempering even further. They use a pretty simple version in the paper, but what if we got more sophisticated with it?
So instead of just a few explorers with different temperatures, you could have a whole diverse team with like a wider range of exploration styles.
Exactly. It'd be fascinating to see how that impacts the AI's ability to find creative solutions, you know, and avoid getting stuck.
Like a brainstorming session where everyone brings their unique perspective. Love it. Anything else?
One last thing, and this might be a bit out there. What if we combined LSA with other cutting-edge techniques? Stuff like hierarchical learning or meta-learning.
Okay, now those sound intense.
Yeah, they are. But hierarchical learning is all about breaking down complex tasks into smaller subtasks.
Gotcha.
Like a to-do list for a big goal. And then meta-learning, that's about learning how to learn. So the AI can adapt to new situations much faster.
So AIs that not only learn efficiently, but can also apply their knowledge to completely new challenges.
Exactly. Combine that with LSA's strengths, you could have some incredibly adaptable, intelligent systems.
Whoa, that's pretty mind-blowing. LSA already sounds like a huge leap forward, and then the possibilities you're talking about, that's really exciting. Feels like this paper is opening up like a whole new world for reinforcement learning.
I totally agree. It's a perfect example of how AI research is constantly pushing the boundaries, you know, and creating all those possibilities. Can't wait to see what happens with LSC, what amazing applications it leads to.
Well, I think we've covered a ton today, from the nuts and bolts of LSC to some really mind-bending possibilities for the future. What are your biggest takeaways from this deep dive? Hit us up on social media. We'd love to hear your thoughts. Until next time, keep exploring, keep learning, and keep asking those what-if questions.